Today we're going to learn how to solve complicated area problems using charts. So, the first problem in the sheet that I had given you is the length of a rectangle. I'm not going to skip all the words. The length is 3 centimeters greater than the width if each dimension is increased by 2, you all have this on your sheet number 70, so if you need something to refer to, that could help you, by 2 centimeters. The area is increased by 26 centimeters. Find the original dimensions. So this may seem like a daunting problem, but in fact, if we use the chart, everything comes out just fine. Keeping track of, as always, is in the area of a rectangle is length, and width always equals area. So in this situation, we have the original, or the first rectangle, and the new rectangle. So going back to the words of the problem, again, this is number 5 on sheet 70. The length is 3 greater than the width. Because the width is mentioned last, we will be calling it x. And the length is 3 greater than x, so it will be x plus 3. What happens in this problem is that each of the dimensions, and remember, dimensions is just another word for length and width, so the length and the width are each increased by 2. When x plus 3 is increased by 2, we now have x plus 5 for a length. And when x in the original width is increased by 2, it's x plus 2. Now I think you pretty much should all remember that length times width equals area in a rectangle. So the area of this, we might not know a number for it, but we know it is length times width, or width times length. It's the same thing. And this one is x plus 5 times x plus 2. Now, unlike some of our other charts, it's not immediately evident how to get the equation. I will say, if we think about this, the area of the first is x times x plus 3. The area of the second is x plus 5 times x plus 2. Now, originally, they're not equal. As we know, the second area is bigger than the first. How much bigger? It's 26 centimeters bigger. In the words of the problem, the original area is increased by 26 to get the new one. So what you have to do is think about what you have. On the one hand, it's x plus 3, and on the other rectangle is x plus 5 times x plus 2. They aren't equal, so you have to figure out what to do to the equation. In fact, we could have, if we wanted to, made them equal by saying, oh dear, taking 26 away from this one. I think that equation is more difficult, so I'm going to go back to my original. But one way or another, we know that equals means equals. It's like the balanced scale. So I know that if I add 26 to this side, I will have the new rectangle. The rest is doing the math that we've been working on, multiplying a monomial by a polynomial, in this case, distributing the x over the x plus 3. And in this one, you have to remember that you are multiplying a polynomial by another polynomial. And so this becomes x squared plus 2x plus 5x plus 10, or when I combine the like terms, So x squared plus 3x plus 26 equals x squared plus 7x plus 10. Again, thinking about the scale, I can take an x squared off of both sides and it will still be equal. So now I've got a plain old equation with the variable on both sides. I need to isolate x. And when I do this, I find out that 16 is equal to 4x, meaning that x is equal to 4. The original dimensions are what the problem asks for. So I plug in this for the original width, and this is the original length. The length and width of both rectangles and then look at it and create an equation based on the facts of the problem. These can be a little tricky, but as with everything else, you'll get the hang of it.